Here's the solutions to homework set number 4 for ECE 376. Now the first problem is how long does C code take to execute? Well, one way to determine that is pick a pin you're not using and toggle it. In this case, I'm going to tie it to a speaker, because if you tie it to a speaker, I can sit there and see the frequency that's coming out. In that case, the number of clocks between toggles is going to be 10 million divided by 2 divided by hertz. So for example, if you want to know how long does it take to count mod 8, what I can do is count on port C, and what that looks like is this. So here it's counting. I've got a speaker with two 100 ohm resistors connected to the various pins, and I get a frequency. And each time I go up a pin is divided by 2. So there's 306. And what I really want is what's the frequency on port C pin 0. And we have a little kitten saying hi, wants to know what's going on. Very curious about this. Okay, so I measured RC5 and got 1220 hertz. That's 32 times the frequency at RC0. So RC0, the one that I care about, is 39 kilohertz, which is higher than I can hear. So plugging in 39 kilohertz into hertz, it is 128 clocks between edges. So that's 128. With this code, every 8th loop I toggle. So take that divided by 8, I get 16. So this loop right here takes about 16 clocks to go all the way through it. And that kind of makes sense. If I had to write that in assembly, I would do increment, move, logical and, then a move, then a go to. That'd be about 6 clocks. It takes 16. So I could do better in assembly. But anyway, that's how long the C code takes. Okay, so that's fun. Let's count mod 7. Doing the same code, counting mod 7, just change that number from 8 to 7, and now suddenly the frequency drops. Instead of being 39 kilohertz, it's only 1000 hertz. Or number of clocks per loop, divided by 7, 698. It takes 16 clocks to count mod 8. It takes 698 clocks to count mod 7. And that seems like a big change for only a very small difference. But what's happening is if I take a number like 1, 2, 3, 4, 5, I misspelled 1, 2, 3, 4, 5, that divided by 100 is really easy. Divided by 100, it's just 1, 2, 3, 4, 4, 5. Piece of cake. Okay, so what is this divide by 9? Suddenly that's hard. That's what's happening with the processor. Powers of 2, mod 8 are easy. I can do mod 8, but just by doing logical and 7. To do mod 7, I've got to sit there, divide by 7, take the remainder, much harder, and that shows up in the number of clocks. Part C, how long does it take to do a long integer division? Same trick as before. So this part of the code takes 16 clocks. We found that on part A. Anything extra is the divide. When I try that, the frequency is 389 hertz, or 12,000 clocks per toggle divided by 8, 1604 clocks per loop. Subtracting out the 16 to set up the loop, it takes about 1588 clocks to do a long integer division. You can do it, but it takes a lot of assembler. And a floating point cosine. Same procedure. Here's a cosine function. A floating point cosine takes about 5,000 clocks. So the PIC can actually do floating point operations. It can do sine, cosine, stuff like that. It takes a lot of clocks to do it, but it can be done. So basically the moral of this story is avoid floating point. A PIC can do it, but it's a lot of clocks. Problem 2 is write a program that beeps. And one way to start is, let's have a subroutine. I'm just going to count 800 times. That's how many toggles. So I've got 800 of these. For each toggle, I'm going to wait 1,000. And the reason for 1,000 is I have no idea what the answer is, so just guess. If I do that, I can use a frequency counter, like piano tuner, and see what the frequency is. I've got 311.6 hertz. To make it 200 hertz, I just scale it. I want the period to be longer, so change that number 1000 to 1588. If I try that again, I now get 200.2 hertz, which is pretty close. For 0.1 second, I just toggle 40 times, 20 hertz, 2 toggles per cycle, 40 toggles, and I get 100 nanoseconds. So this is what that program looks like. I have it playing beep, and I'm counting to 100,000 in between, just to waste time. Next problem. I want to get a roulette wheel. So here's what the roulette wheel should look like when you're done. So when the code's finished, I want this. The number I press is the number I'm betting on. So if I want to bet on 3 or 2, I just bet on number 2. Here's the number on the roulette wheel. The winning number was 7. So I lost, and my bank goes down 1. Try this betting on 3. And I lost. So how do you program that? Well, first let's start with the flowchart. I'm going to start on reset with $10 in my bank. I'll then display the bank, wait for me to hit a button. You pick a button, any button over here. When I hit the button, it waits for me to release the button, and it's going to count really, really fast, mod 8. The final count is my winning number. The button I push is the number I bet on. I am then going to tell it how many times I want it to count. There'll be 40 plus n. Each count, I'm going to display what number is up, where the ball is, beep, waits, decrement x, keep going until I get to 0. When I get to 0, I'll check, is the number I bet equal to the winning number? If so, I won $8, otherwise lose 1. So again, here's kind of what it looks like, betting on a 4 or 3. Winning number was 7, and I lost $1. Let's bet on 0. Winning number was 7, and I lost again. Okay, so that's the code. Converting to C, here's my beep routine. I sped it up a little bit just because it was getting kind of annoying. The main code, I start it with $10 in the bank. I then wait until I hit a button. 0 is false, anything non-zero is true. So wait until I hit any button, pick a button, any button. While I'm holding a button down, count mod 8 really, really fast. And I want to know which button I pushed. One thing I've kind of found is you can do almost anything with an if statement. This isn't stylish, but it tells me which button I pushed. Keep going until I release the button. Once I release it, I've got the number I bet on, I've got the winning number, and I display. Here's the number that I bet on. Then count 40 plus n times. Each time I count, display. Here's where the ball currently is. Beep, wait 100 milliseconds. And then when I'm done, display, here's where the ball is. If I won, add $8 to the bank. If I lost, subtract 1. So again, I'm going to bet on the number 4. So right here, this is the number 4. My screen locked up. There it is, the 4, and the winning number is 3. I bet on a 2. Here's the number. Lost again. So to verify your code, go back to the requirements, make sure you met all the requirements. On reset, I started with $10. That checks out. And I'll show you that in a sec. Go back over here. As you can see in the corner, I hit reset. And there's my $10 bank account. The LCD information is correct. I've got the correct bank balance. I keep on losing. I did win occasionally. Each time I win, I got $8. The number that I bet on is correct. I hit the 1 key. My bet is on number 1. And it is correct. If the number 1 comes up, I win $8. Otherwise, I lose $1. And for the demonstration, be in person with a video, kind of your pick. When I'm all said and done, my final code is 1,563 lines of assembly. This is a code that I wouldn't really want to write in assembly, but that's the beauty of C. It's not that hard a program to write in C. Be really painful in assembly. That's why we use C code. It is much, much easier doing some things in C code. C really frees you up, makes coding a whole lot easier. So we really like C. And that's one solution for homework set number 4 for ECE 376.